So, morning everyone, welcome. Well, I'm not very good with speeches, so I'll leave.
I'm leaving Lenny to say a few words.
I'm not sure it's because they like your speech or because
They clearly like Lenny.
yeah.
So, welcome everyone, and I wanted to thank in advance Maxime and Marco for all of the hard work they did to put this together.
That's a little ominous.
Okay, well, we will postpone that until the end. They really put in a lot of work for this, and also they are responsible for anything that goes wrong. So, I just wanted to say a couple of words as historical words, because I'm older than almost all of you, about Legendary contact homology. So this is a subject that I find really exciting, and hopefully you will or do as well. So back in the day when I was a graduate student, there were lots of Floer theories flying around, and they measured various geometric things. And they all sort of suffered from a single problem, which was that none of them were computable because they were not combinatorial in nature. And I think, Legendrian contact homology was one of the first ones that was in some way combinatorial. So this was this paper of Chekhanov that came out in the late 90s and really changed sort of the subject. So that was one of the things that drew me to it. It was that here was some theory that you could actually compute, but it had some really serious geometric content in it. And nowadays there are many other Floer theories that are combinatorial, but we will ignore all of them. Since then, this has really turned into some sort of very diverse field with sort of something for everyone. So for instance, if you're interested in contact knot theory, if you're interested in Legendrian and transverse knots, this is one of the key tools I think that is used to study them. If you're interested in smooth knots, then you might be interested in knot contact homology. This, by the way, is just turning into an advertisement for various things that will be coming this week. So this is some sort of invariant of smooth knots, which is quite strong and is a special case of Legendrian contact homology. That in turn has relations to various things like character varieties, representations of the fundamental group, and sort of most interestingly, at least to me, and most puzzlingly, is there some sort of correspondence to physics and Honfley polynomials. And this is through topological strings, topological string theory. So this part is still rather murky, and it's an area of active research, at least for us on the math side. I think in the physics side, they sort of got interested in this a few years back, and they've now zoomed past this and are doing something completely different. But I think this is something that is pretty nice. Some other things that it's related to that you may know about. So through augmentations, there's some relation to constructible sheaves. So if you're interested in algebraic geometry or mirror symmetry, I guess there's some close relation in this way. And along similar lines, if you're interested in symplectic topology and again mirror symmetry, there's some nice way of using Legendrian contact homology to compute various symplectic invariants. So for instance, one that I think we'll probably hear about a bit is wrapped Floer homology. There are various surgery formulas and ways that you can understand symplectic manifolds or Fukaya categories through this. Okay, so these are some of the things, some of the ways that this subject that started off pretty small has sort of grown and wrapped its tendrils around various other subjects. And I think that's actually, in some sense, I've written 5 things on the board, and these somewhat correspond to the 5 days that we have here. So anyway, that's a little outline of hopefully what's coming, and I will be here the whole week. I'm not an oracle, so I may have answers to your questions, but I may not. I'm hoping to learn some things as well, so we'll see how this goes. That's it. And now we have Marco to start things off.
Yay. Do we have any announcement, any particular announcement that we know of? Maxim?
the moment.
Okay, great. Good. So, without much further ado, today, well, as Lenny said, these are the topics for the 4 days. Today, we're going to look at Legendre homology, and I guess that one cannot start talking about contact stuff without defining what a contact structure is, what a Legendrian thing is, and then we'll move on. And for now, we'll look at things in R3, or Legendrians in R3, and their variants. So, right. We are in R3, and in R3 we have the standard contact structure. People in the back can read. People in the back can hear me. Since it's the only contact structure that we'll see today, we're going to call it Xi, and that's it. This is the kernel of the standard contact form. It's the only contact form that we'll see, so it's going to be alpha. That's not true. And alpha is dz minus y dx. So what does it mean to be contact? So it means that alpha, where's the alpha, is positive at each point. Let me say that one could do something slightly different with alpha and use alpha prime, which is sort of a symmetrized version. X dy minus y dx. That's sort of the same contact structure, but with a different kind of symmetry. That's useful if you want to think about open books, and especially the standard open book on R3. Right. Of course, one can do things in higher dimensions as well, and instead of having y dx, one can sum over all coordinates, where r2n plus 1 has coordinates x1, y1. Maybe I should write. Yeah, x1, y1, xn, yn. Okay, good. What do we care about? We care about Legendrian things. So, a Legendrian, not lambda in R3 is an embedding. So let me restrict to knots instead of links, just because I don't like high numbers. Is an embedding lambda from S1 to R3 such that tangent space lambda is contained in the contact structure. So I'm a low-dimensional topologist. I like knots and I like diagrams. So I want a way to represent Legendrian knots. And well, in knot theory, usually you just have a generic projection and you look at double points and you understand what things like by looking at undercrossing and overcrossings. For Legendrian knots, one needs to be a bit more careful, and there are two ways to represent them. And they are the front projection and the Lagrangian projection. By the way, for the record, this just goes through in high dimensions as well, where you use 2n plus 1, and you have an embedding of an n manifold into R2n plus 1 with the same condition. Luckily, in dimension 1, there are not so many connected manifolds, and one can use S1 instead. Right, so there are two ways to represent them, and they correspond to two different projections. So this corresponds to the projection. I will drop the front I will drop the name of the projection later on, but at least for this board. X, Y, Z goes to X, Z, and the Lagrangian sends X, Y, Z to X, Y. So these two projections exist also in higher dimensions. This one forgets almost half of the dimension, and this one just forgets one. So they get a bit harder to draw. At least this one is still drawable in dimension 5. These ones, I won't even try. So how do things look like? Let's look at the front projection first, maybe. So about the front, what do we know? The only thing that we know, maybe let's not call this lambda, let's call it beta, and let's switch back to S1 into R3. What do we know about beta? We know that the derivative of beta is killed by alpha. Alpha is dz, is alpha here. So we know that d over dz, sorry, this doesn't make sense. So the derivative of beta in the z component minus beta y times the derivative of z in the x component is how they satisfy this condition. And this means that basically if you look at dz over dx in the projection, this is y, the long projection. And in particular, this means the projection cannot have, the front cannot have vertical tangencies. So one would be tempted to draw a knot like this, except that I screwed up. One would be tempted to draw a knot like this, but one cannot have vertical tangencies, and instead, these are forbidden, and instead one replaces them with cusps. So what one would see is something like this. Now, I have suppressed something because this equation tells us something more. Not only it tells us that we cannot have vertical tangencies, but also that the higher slopes, the higher y coordinate, correspond to higher slopes. So whenever I see the crossing, I already know where the smooth what the smooth projection would look like. So here, let me redraw it. Here the higher slope is this one, so this one goes up. Now, there is a bit of a problem, which is something that I really, really hate and I really struggle with a lot of times, that the triple x, z, y induces the wrong orientation on R3. So, if you use your left hand, it's fine, but that's not the purpose. So what happens is that actually this is a diagram for the trefoil, but if you look at it smoothly, it's a diagram for the left-hand trefoil instead of the right-hand trefoil. So I think that what the right thing to do is to actually sort of project with y going into the blackboard instead of going outside the blackboard. So the higher coordinate has, the highest y coordinate has high slope, but it also means that it goes beneath. So what actually one should do is revert all the crossings. Basically, I cannot do this without double negations. But, so this is the right picture, and this will turn out to be useful later. The cusp thing, one can draw them with horizontal slope, and it's something like a generic phenomenon. You don't need to worry too much about what happens. Right. I'm a topologist, I'm not a geometer, so I like things when they are a bit flexible, when you can move them around a bit. I don't care about any given embedding of a Legendrian, and you should not care about any given embedding of a Legendrian, at least because I tell you so. But I care about the isotopy class of this embedding. So, knots will always be considered up to isotopy, and the notion that we want to look at, so Legendrian knot, up to isotopies through Legendrians. Right, and then one can ask, if I give you two projections, so I gave you one way to construct a knot, to construct a projection given an embedding. And by the way, this equation tells us that the knot itself, the embedding itself, is reconstructed from the projection, which is something very, very different from what happens in the just in the smooth case, where heights can go up and down. It's a bit of a mess. You can't reconstruct the embedding. This actually reconstructs the physical embedding, but then we want to know what happens when we have an isotopy. And so, how does the projection change? In an isotopy, and there are roughly three things that can happen. Is it legible?
At least it fits into the frame.
Okay. That's something. Right, there are a couple of things that can happen. So probably you're familiar with the Reidemeister moves in the smooth setting. What happens is that you can have sort of a straight piece of diagram, and you add a kink, or a Legendrian kink, and back. You can have a Reidemeister type 2 move, where something like this happens. And a Reidemeister 3 move, well, that doesn't change really from the smooth case. Right, and one might wonder, well, these seem to be pretty restrictive. Why did you ever write the Reidemeister 3 move, the Reidemeister 2 move in this way, instead of taking the easy way around? That would be... That would be taking two horizontal strands and then pushing one up. Well, because of what I just erased, recall that smoothly, this goes up, so it's higher slope, so it's back in the board. And this is lower slope, so it's front. Did I just say? Yeah. I just did the opposite of what I said, of course. And this one does the opposite thing. So what you would see if you try to do it this way wouldn't even be a smooth isotopy. You would be crossing the strand when you go up. And likewise, one could try and think and say, oh look, I have a cusp, and then sort of add a kink here. So one could think of doing something like this. So smoothly, it looks like the same thing, and smoothly it is the same thing. This is a smooth Reidemeister move, but as we shall see very, very soon, these two things are not Legendre isotopic. So this is not even smoothly isotopic. This is not Legendre isotopic. And the reason is that when you try to undo the kink, if you try to draw the projection, at some point you're trying to create a vertical tangency when you try to collapse this thing, or when you try to flip it. You're sort of creating a vertical tangency, and that's sort of bad singularity of the Legendre isotope. Right. So, how do we distinguish between two Legendres? One thing is having moves to go from one projection to the other. That in principle tells you when two things are isotopic. But effectively, I mean, if you've ever played around with Reidemeister moves and not projections in the smooth case, you know very well that it's sort of hopeless in general to go from one knot to the other unless you know that they are the same, or you have, unless you're a magician of some sort. So it's good to have things that tell knots apart. And the first thing that tells two Legendre knots apart, so lambda, maybe I will use the tilde just to denote isotopy. Yeah, maybe, yeah. This is Legendre isotope for this topic. Then, in particular, the smooth knot types are the same. This is sort of the stupid invariant. But now we want to have something refined. Something, for instance, that tells us right away that this move is a bad move. And so we define the other two classical invariants. So Thurston-Bekan and rotation number. So how are they defined? Well, we should try and use the contact planes in some way. So to define the Thurston-Bekan, let me do it maybe in a suitable way for what I'm going to do next. So let me define what a red field is. A red vector field R is a vector field R such that alpha of R is constantly 1, and if you take d alpha and you plug in R, you get constantly 0. You can play around and find that this vector field is unique. It's also unique in higher dimensions. This is sort of a uniform definition, and you can have fun and show that R for the standard contact form, the one that was up here earlier, is actually d over dz. You can check that it works, but also checking that it's unique is alright. And we can use this to define invariants. So what do? We take a knot. So we take a Legendre and we push it off using R. We just push it off a bit and obtain what I call lambda plus. And now we have two knots in R3, and we can ask what their linking number is. So the Thurston-Bekan invariant of lambda is the linking number of lambda and lambda plus. Theoretically, all is good and well. If we can compute it, as Lenny was saying, sort of hinting at, then it's useless. So let's try and figure out a way to compute it. So, in the front projection, this is reasonably easy because the front projection has z going up, x staying here, and the vector field just pushes things up. So if we have a projection here, this is lambda, and it's high time for colors. Lambda plus is going to be just pushed up in a vertical direction slightly. So this is lambda plus. And now we need to compute the linking number. Well, now we remember that this is actually an overcrossing of the blue. This is an overcrossing of the black. And so the linking number is equal to -1. This is oriented and it induces an orientation here. Or even if it's not oriented, any orientation here induces an orientation here, and the linking number is independent of the choice of the first orientation. If you reverse both orientations, you get the same thing. So this means that the Thurston Bencan of this knot is -1. So for future reference, this is the standard Legendre knot. By definition. Right. Good. Also, notice as I said that TB is an invariant of the unoriented knot type. We can squeeze out still a little more information. And well, this is already enough actually to show that this move is not a good Legendrian move, because if you take, well, if you apply this move to this knot, then you get this projection. If you push it off, you get this projection. And now you see that at the cusps, you get the same contribution, but then you get an extra linking from here. So Thurston Bencan of this knot is -2. So this is already enough to tell apart this knot and this knot while they're both unknots. Good. Can we actually squeeze out a formula for this? Well, yes, we can. Exercise. Can you read down here from the back? No. That's a clear no. So maybe exercise up here. So TB of lambda is the right of the front of lambda minus 1/2 the number of cusps in the front. So it's something that one looks at the diagram, one doesn't even need to draw the push of lambda plus, just looks at the diagram and computes it. Right. There's one more invariant that we can squeeze off, where we actually consider the orientation coming in. So, by the way, this generalizes in high dimensions as well. You can take the same definition, and in half of the cases you get something interesting, in half of the cases you get something boring, but that's a different story. So let's stick to dimension 3 where I'm more comfortable. Right, so we have the rotation number, where you take a trivialization. So lambda, T lambda inside of psi induces is a trivialization. Of psi restricted to lambda. Now in dimension 3, lambda is the boundary of a surface called the Seifert surface. And a Seifert surface is a surface with boundary. So compact with boundary. Let's call it F. So psi restricted to F is a two-plane field on a surface with boundary, so it's trivial. And the rotation number of lambda measures the non-triviality, or rather the non-extendability of the trivialization, let's call it S, of S. So in other words, it should be something like the Euler number of psi restricted to F measured with respect to the trivialization on the boundary of F. And this does indeed depend on the orientation, because if you, a priori at least, because if you change the orientation of lambda, then you change the trivialization, and you expect this to change psi. So whenever this invariant is non-zero, when you flip the orientation, it changes. It changes psi. How do we compute this? Well, we're lucky, because in dimension 3, in the standard contact structure, we have sort of a global trivialization. So we can move things around. We can take a trivialization of psi f, of psi restricted to f, and measure how much the trivialization given by lambda twists with respect to this fixed trivialization. And it turns out that on R3, we have a fixed trivialization for every Seifert surface. It's globally trivial, so you can take a global trivialization and see what happens. And the global trivialization, maybe let me leave some things on the board. I want to play with these examples a bit more. So, all right. The global trivialization, d over dy is a global trivialization. Of psi. And what happens is that we're measuring how many times the tangent space to lambda goes through the plane, goes through this vector field in psi. And if you think about it, this counts how many cusps you have going up or going down, because the point where you cross, where your tangent space crosses dx over dy is a horizontal slope. So the rotation number of lambda is 1/2 of the number of cusps going up minus the number of cusps going down in the front. I might have screwed this up.
That's backwards.
Right. I don't think that we'll care at all about the sum. But
So just to check that I'm understanding, is this backwards because measuring the trivialization of the boundary relative to the interior versus interior relative boundary flips the sign? This is to detail the question.
I think there are two orientation conventions. I mean, you need to understand what means going in the positive, crossing in the
Right.
positive, and what it means to go up and go down with respect to this. So, if you think, I won't be able to do it on the black.
Yeah.
Probably not even with a piece of paper in 2 hours, but that's a different story. Right, so let's count things. So here the rotation number.
Actually, I have a simple answer, which is just, so for instance, if you have an up cusp, a right up cusp, then you're going from y positive to y negative. The slope is going from positive to negative. So it looks like the cusp is going up, but in fact, you're crossing,
Ah, right.
yeah, downwards. Okay.
Thanks. So the rotation number here, let's pick this orientation. We need to pick one now. you have one cusp down and one cusp up, and regardless of the sign here, the rotation number is 0. If you do this example, then the rotation number, for people in the back, so the rotation number of this, let's say we pick this orientation, you're going down, and then you're going down again. So this is, according to this is 1. Good. So very, very quickly, the Lagrangian projection is a bit easier in the sense that pretty much whatever you draw, you can't decide whether it's a Lagrangian projection or not. But at least you don't have sort of immediate topological obstructions like no vertical tendencies, and you have no way of determining whether a crossing is an undercrossing or an overcrossing just by looking at the projection. So Lagrangian, no cusps or other oddities.
Excuse me, maybe I'm confused now, but so the first American number just depends on lambda only, but rotation number doesn't that depend on the orientation? Of
Yeah.
the so,
Yeah.
Which arrow do you put there?
So I mean, then you have to check, you have to choose an orientation, let's say.
Yeah. This is oriented. This is an oriented invariant.
In this picture, we're computing the rotation. Maybe we just can't see.
Yeah.
Is it,
So yeah, sorry.
Okay,
So I picked an orientation,
all right.
which are one that I prefer,
Ah.
and then this is oriented to begin with, so it has an orientation. Let's say that it's that orientation, and then I count cusps, and they're both going down. And if I change the orientation, then the cusps go up,
Yeah, right.
and so the rotation number changes. Yes, absolutely. Right. So in the Lagrangian projection looks a lot like any projection. There's a weird condition on the areas, or something like an area. So this will maybe be useful later. So you have that the integral. So suppose you have a parameterization as before, 2R3. Then the condition is that the integral of y dx over the whole S1 vanishes. What this means is a bit mysterious. Basically, it means that the knot has to close up. And once you have a diagram that satisfies this condition, then the knot is reconstructed up to vertical shifts. So it's basically rigid except for vertical translations. This doesn't see the red vector field. So I maybe leave as an exercise what happens. So as an exercise, one can compute, maybe let's draw one front. It will appear later as well. But let's draw one front. This is the Lagrangian projection for the trefoil.
Okay, so then the two
Yeah.
right and those are backwards.
Thank you. And probably you need to make these things a bit fatter to ensure that this condition holds, but you can deform a projection like this through isotopies, through smooth isotopies in order to achieve this. For what we care about, this will do. Right, so exercise, the Thurston-Benkham lambda can be computed from the front. It's just the right of the front of the Lagrangian projection of lambda, and the rotation number can be computed as the winding number of the Lagrangian projection. So you look at the tangent vector and you measure how many times it goes around. Right, so for this one, I will not do the computation, but you can check that these three have the same sign, these two have opposite signs, and TB of this is +1, and the rotation number, well, you play around, and this is 0. Right. Why do we care about these? Well, because now we have three invariants, and we can ask, how much do they determine of the knot? In particular, are they complete invariant? If I have two Legendrian knots with the same classical invariance, are they ever the same? Sometimes they are.
In the same smooth.
In the same smooth case. Classical invariance includes the knot type. Right, so the big question is, do the classical invariant determine lambda? And maybe to give a bit of context, maybe not, a little history maybe, the answer is yes for certain knot types, and these are called Legendrian simple knot types. So it's true, so the answer is yes for the M knot. Let me not write down names, this is a Jashberg and Fraser for torus knots plus the figure 8. This is John Etnayer and Kohonda for twist knots and certain cables. I think I should throw in Vera Berteschi and Bulen Tosson at some point later on for some of these.
For the word certain should be in front of twist knots also.
Yeah, for these later two, I think. At least this should be Etnayer, Honda, and Berteschi, I think. Isn't it?
It replaced co by me.
Oh, sorry.
I basically did none of the work, so it's okay.
But then I didn't. Okay, good. I screwed up history. That's the only thing I didn't. Well, it's not the only thing I didn't check. Right. Thanks, Lenny. Good. And you also have the sort of geography problem. That is, which kind of invariance can you realize? Can all pairs TB and rotation be realized? So let's look at one operation that one can do on Legendrian knots. So one can always mess with the Thurston-Bencan and rotation by doing exactly what I was forbidding you to do earlier. That is by replacing a cusp with this, or by adding a zigzag. That is, you take a horizontal piece and you add a zigzag. You can do the opposite zigzag. Or in the Lagrangian projection, which is maybe what we will care about more later. So this is front, and this is Lagrangian. You can add a kink. Each of these operations, these two are slightly different. This depends on the sign of the cusp. This depends on, I guess, the flip that you make. Right. These are called stabilizations. And the net effect is that TB goes down by 1. And rotation changes by plus minus 1. This is easy to see in the front projection, in the Lagrangian projection, for instance, because you add just one crossing. So the right, oh, actually you need to add, oh, this is determined. Crap. Right. No, you can't do this. You have to, yeah, you have to do this. The other one was not good. And rotation changes by plus or minus 1. That depends on the orientation of the set. So this can go up or down. And then rotation changes by plus minus 1. In particular, well, one can observe that TB minus rotation has always the same parity under stabilization. And in fact, it's always true that TB minus rotation, we exercise. TB minus rotation is always odd. And this tells you, well, you can take a knot, you have your TB and your rotation, that's the point on the plane, and you can always go down, sort of skipping the ones with even sums, and you can always get a sort of tilted quadrant going down. can you always go up? Can you always go sideways? Can you do weird things? And the answer is no. And some refer to this theorem probably as the birth of modern contact geometry. So, theorem, I can e2 TB of lambda minus rotation number of lambda is always less than 2g of k minus 1, where k is the knot type and g is the minimal genus of a Seifert surface for k. So recall earlier that I said that there was a Seifert surface, but for each Seifert surface that inequality holds. And if one puts in Rudolph here, I believe it's 95, one can refine this to talk about the 4 genus, which is the minimal genus of the Seifert surface inside the 4 ball, instead of the minimal genus of a Seifert surface in R3. There are refinements of this, sort of Floer theoretical refinements of various sorts, but these were the first inequalities. And actually, since this holds for both orientations, one can put an absolute value here, or put a plus. And this tells you that you are always in a certain quadrant down here. And there are other refined inequalities, and things can be pretty weird. But let me not go too deep into that. Right, so this is for the question of geography. Now for the question of botany. How do we tell, let's say that we have 2 knots that have the same classical invariance. How on earth can we try and show that they are not Legendre anisotropic? We need some stronger invariant. So we'll look at Legendre contact homology as defined by Chekhanov. And this is going to be a bit weird. So it's going to be a DGA. So differential, graded algebra. So we need to associate to any Legendre knot an algebra, equip it with a grading, and then with a differential. And hopefully we want to do it in a combinatorial way. So good luck. And Chekhanov was inspired by SFT ideas and sort of combinatorialized, as far as I understand, he combinatorialized some SFT ideas. What do? So you take a projection, the one that I just erased, very conveniently. Is this still the right one? Yes. What do? So you associate, you take the free, so the algebra is free, non-abelian, unital, over F, the ring with 2 elements, field with 2 elements, generated by double points in the Lagrangian projection. So in this case, we have, for this trefoil, we have 5 generators, one corresponding to this double crossing, one corresponding to each of the crossings of the projection, and traditionally they are called A1, A2, B1, B2, B3, and I will make no attempt of changing the notation. This is sort of what you find in all papers about this. And great, we have an algebra, check. We want a grading, so we grade generators. And then sort of multiplying things, add things up. So we need to define the grading of, say, A1. What we do is we take a path that goes from A1 to A1 along the projection, and we measure how much the tangent vector twists. So what do? We start with the vector that goes here and goes up, 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 and then it goes almost all the way back. So this is clearly impossible to understand. So let me try and follow things here. And then it goes back, and we need to fix a way to close things up. And the way we fix things up is we roll things back clockwise until we meet the same direction. Now, I've been a bit careless. What we're looking at is the direction and not the oriented direction. So we measure how many times we cross this initial direction when we go around the loop. And what this means, we cross it here once positively, and then we're almost all the way through, but then we go back clockwise. So what happens is that by the end of the loop, we crossed it exactly once. So here, the grading of A1 is 1. Because it sort of winds half plus epsilon, and we count that half, basically. The same trick, ooh, exciting. The same trick works for A2. And for B2, B3, and B4, well, B1, B2, and B3, you can have fun. Oh. Did the power go off?
I think the power went out.
Ah, okay. Well, can you still read? Vaguely? Maybe I'll try and change marker. So, for the others, it's sort of the same, it's just longer loops. Don't try to get you to read. But you'll find out that the gradings in this case is B1 equal B2 equal B3 equal 0. Right? And notice that there's an ambiguity. I've chosen a path. What happens if I choose the other path? What happens is that the difference between the two gradients that I obtain is exactly the total winding of the front projection, of the Lagrangian projection, well, multiplied by 2, because sort of I counted half twists instead of full twists. So the grading defined up to twice the rotation number of lambda. So it's not an integer grading, so it's a z mod 2 rot lambda z grading. Oh, yeah, it's fine. You can get rid of this. You can actually lift it to a z grading at the cost of changing the algebra over which you define things, and you can also lift to integer coefficients. This was done by Lenny, John Ednayer, and Sabloff. Right. So differentials. As usual in Fluor homology, algebra and grading, not so bad. Differentials, sort of a mess. So delta counts immersed polygons in the plane. And what kind of polygons does it count? So if you want to look at the differential of A, so let's say you have A, then it's a crossing in the diagram, and the crossing comes with two distinguished regions, plus and plus, which is the ones that you sweep from the overcrossing, from the overstrand to the lower strand by going counterclockwise. And, well, the other ones are called negative. And the differential counts polygons, so sum over polygons, maybe sum over k, over sum, let me write the formula. maybe. Times b1 times bk. So you need to spit out an algebra element, so I need to give you a sum of monomials. The monomial is a product of double points. Which double points are they? They are, okay, let's maybe do an example. They are polygons with k plus 1 vertices. They are immersed in a plane, and one of the vertices goes to A, and it occupies one of the two plus regions. And at every other crossing, the only thing it can do, it can either go straight or turn left at a negative crossing. What does this mean? So let's look at this example. So, well, that's a stupid example in some sense, but so A has two pluses, A1 has two pluses, and here you see an immersed one-gon in the plane that has one positive corner at A1. So this corresponds to the empty word here. So this polygon contributes to delta of A1 being 1 plus something. So now we need to try and count the other ones. So this way we have no hope of finding anything else. We're sort of closed down. So we go back, we try the other way, and we start. So now the crossings are all the same, so they're all somehow horizontal. So we follow A1 and we get here. When we get to B1, we're in negative region. We can do one of two things. We can go straight or we can turn left. If we turn left, we hit this boundary and we record the B1. So let's say that we turn left. Maybe I should redraw the picture and make it a bit more sensible. Where did I?
Sorry, I missed the part about when you enter left, only at a negative.
Only at negative edges, yes. So let me redraw the upper part of the diagram here. So this is the region that we're, or maybe the two regions that we're considering. The upper half part. So if we turn left, this is a negative, 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 positive. Here we can turn left or go straight. Let's say that we turn left, and at this crossing we can either decide to go straight or to turn left again. And if we go straight, we go back here. So if we go straight, we see the beigen. So this is not a curve. We see this region with 1 plus and 1 minus. And this is B1 and this is A1. So this tells us that B1 is a summand in the differential of A1. Or we can turn at this crossing again. So we turn here and we turn at the next crossing too. And so we see plus, minus, minus, B1, B2, B3. And we see that B1, B2, B3 is one of the summands in the differential. Notice that the order is important. This is a non-commutative algebra, so the order is very, very important. The other thing that we could have done, we could have gone straight here. So what happens if we go straight here? Then we arrive at this crossing, but we arrive at the positive, so we cannot turn left, so we must go straight. And then we arrive here, and we're at negative, and we can turn. We cannot go straight, because I've been a bit sloppy, but we cannot turn straight. But here you see a beigen with a B3 and an A1, and so this has a B3 in the sum as well. Well, any differential that deserves this name must drop the degree by 1. So this is a good way of telling, for instance, immediately that A1 must have degree 1, because, well, we want the unit to be in degree 0. So if we have something whose differential contains a 1, it better be of degree 1. And then it tells you that B1 and B3 have the same degree as 1, so they must be in degree 0. And B1, B2, B3 is something that has to have degree 0. These two have degree 0, so B2 has to have degree 0 too. So if you don't want to compute the differential like initially from the diagram, you can still hope to reconstruct it by looking at the differential and hoping that things work out. It doesn't always work out, but sometimes. In this case, it determines pretty much everything on the nose. Right. Yay, we have something computable that's defined combinatorially. You can convince yourself, well, maybe I should say that here, Chekhanov, that AD is an invariant of lambda, right, and well, D decreases the grading by 1, and D squared is equal to 0.
Do you want to say something about what you mean by an invariant?
Thank you. I wanted somebody else to say that. Because I've been cheating you, clearly. Because I never told you it cannot be an invariant. Because if I have two projections with different number of crossings, you have two algebras that look completely different. So they cannot be the same. So the right concept of being invariant is something called stably, tamely isomorphic, I believe. So invariant means up to stable, tame isomorphisms. It's gonna be talked about a bit later, but the idea is that you have elementary. Should I write that far down? So you have elementary automorphisms of an algebra that are of the form, well, this algebra has a set of generators, of distinguished generators, and it's of the form AI goes to AI for I different from, let's say, 1, and A1 goes to A1 plus something in A2 through AN. And maybe together with permutation. So you can permute the vertices, so you can move things around. And then you can stabilize by adding a generator. And what do you want the differential to do on the new generator?
Two new generators?
No, I think you want to add 1.
It's 2.
It's 2, great. By adding 2 generators, and presumably the only thing that you want to do is A nu is equal to A nu prime. And you say the two things are stably isomorphic if they differ by a number of stabilizations, automorphisms and then isomorphisms that preserve the differential on them.
Don't we also knew that the differential of E nu prime is 0?
Well, this is automatic from here. Yeah. If you want this square to be 0. Yeah, sure. Right. Any other questions? Good.
This stabilization, does it have something to do with the stabilization of the knot? Just because of the name, so that people don't
No.
get confused?
No, but I want to state something and maybe try and give a proof. If I can, I maybe won't state in 5 minutes. But it's great. We have an invariant. It's computable, and now we just have to say whether two things are isomorphic or not. Well, good luck. It's a mess. This thing is a non-commutative algebra with a differential. What the hell are you supposed to do with that? There are a few things you can do, in fact. Neither of them is particularly easy. You can take homology. So kernel of delta divided by the image of delta, except that now you should be careful because you're in a non-commutative setting, so you should take the two-sided ideal generated by the image of delta, and again, good luck computing things with that. You can take something a bit larger, which apparently means more complicated. You can take the characteristic algebra, which is what Lenny defined. So you can take the whole algebra, mod out by the image of the differential, and hope to compute things in there. And Lenny has used it sort of efficiently, at least in some examples, and he claims that it's something that you can implement on a computer and play around with. You can look at augmentations that will be talked about a lot later, I suppose. And other than that, you must be smart. That's the only thing I think you can say. Let me state one result that maybe is useful and motivates a lot of questions in the area. And yeah, at least, let me state it here. So, Chicano. If lambda is stabilized, that is, it has a kink in the Lagrangian projection, then LCH of lambda vanishes. What is LCH? So definition, LCH of lambda is the homology of a delta, that is the kernel delta modulo two-sided ideals, image of delta. And in fact, there's a refinement due to Lenny that under the same assumptions, in fact, A mod the image of delta is trivial.
So by stabilization, you still mean the same thing,
I still mean, no, this is now the Legendre stabilization.
Okay, that's zigzagging.
Yeah.
Yeah.
Yes.
What's the proof? Well, the proof, I will cheat and I will give you a proof. If you add a kink, then you see a 1 gone immediately. And this tells you that the differential of this new generator that you introduced is 1. I'm cheating. Don't look at me funny. I'm cheating.
Was that you?
Yeah, also. She was very perplexed. Because you can claim and say, but look, there's something that looks like a kink here. And yes. But what I told you is that the Lagrangian projection is very delicate. There are things that we don't see immediately from the smooth Lagrangian projection, which is areas and distances, vertical distances between points. When you introduce stabilization, you can make this height difference as small as you like, and make sure that this actually is the only polygon that you count. So this is related to the condition that I had written down sometimes back and that I can't see anymore, about the integral of y dx having to be 0 all over the place. What it actually measures, if you take the integral of y over this area of this arc, is the difference in height between these 2 points. And basically, you use Stokes' formula, and it's very appropriate that I say Stokes, since yesterday was its 198th birthday. But yeah, you measure. Thanks.
How did you know this?
I think it's Quantum magazine that sends these flashes at times, or something in my Facebook feed that flashes out these things. So I thought it very appropriate.
His friends on Facebook. So.
Yeah. Right.
Yeah, and so actually this is actually true, and this holds for stabilizations, but not for things like this. The fact is that when you have a stabilization, you actually don't see these big.
But maybe the front projection is really more suitable with this. So you don't see this fish tail or whatever it's called. I don't know in that front projection. But there you see it.
Yeah, but you have to.
This what do you call it?
The zigzag.
Exact.
No, the
Zigzag,
kink.
this
The
guy.
kink.
The fish tail.
Yeah.
You
Okay.
see that there, but you don't see it there in the front.
Yeah.
And when you see the fish tail, you can actually shrink the fish tail.
Yeah.
Relative to its boundary.
Yeah. Maybe I should say that Lenny gave a reformulation for front projections, but for some reason I was lazy.
No, but I mean, you can see it here also, because if there were anything going off to the left, then it would also persist when you get rid of that kink there, and that would be a disk with all negative corners, which is forbidden by Stokes, I guess.
Yeah, it's sort of the same. Yeah. Right, so now you have a question. Have fun with it. Is it true that if LCH vanishes, then lambda is stabilized? Or is it true that if lambda cannot be destabilized, then its LCH is non-vanishing? I won't tell you. Right. Coffee break?
Yeah, I guess till 11:10, about half hour.
Great. Other questions? No, don't try now.
I have one comment.
Yeah.
Right. So whenever you have two diagrams, and you don't really know if they represent knots in the same smooth type, then sometimes, according to the theorem, right, sometimes classical invariants beat Legendrian contact homology because Legendrian contact homology vanishes as far as you have something stabilized. But classical invariants can't always beat.
Yeah,
Sure. That's just as a comment.
Yeah, has everybody gotten Roman's comment? Sometimes, what he said is that basically sometimes classical invariants are finer than Legendrian contact homology simply because when you stabilize, everything dies in this setting, but not everything dies in the smooth setting. But in some sense, what you're interested in when you look at classification is what can you do when things are not destabilizable. So you want to look at the top strata in some sense. Yeah. Absolutely. Great. No. What? Shut up. What?